Imagine looking up at the night sky. It is vast and dark, but scattered across that darkness are points of unimaginable power. Stars shine with the energy of 1 billion nuclear bombs every second. But there are other things out there, things far more powerful. They are black holes. They are places of ultimate collapse. They are also, perhaps, places of ultimate energy. We live on a small planet with a growing need for power. We worry about fuel. We worry about climate. We argue over resources. What if we could solve this problem forever? What if we could reach out and tap into the most powerful objects in the universe? This is the question we will explore. The idea sounds like science fiction. It is audacious. It is grand. But it is rooted in real physics. The laws that describe black holes also hint at ways to extract energy from them. For decades, some of the most brilliant minds in science have pondered this. They see not just a cosmic mystery, but a potential cosmic battery. Our civilization is built on energy. From the first fire lit by an ancestor to the vast electrical grids that power our cities, our story is a story of finding and using energy. Our future depends on finding much more. And so we must look to the stars. We must look to the strange, dark, and powerful heart of the galaxy. Imagine a future where our energy crises are solved not by solar, wind, or even nuclear, but by something infinitely more powerful. What if the answer to humanity's insatiable energy demands lies within the most mysterious and destructive forces in the universe, black holes? Prepare to have your mind expanded. So, what is a black hole? It is what remains when a truly massive star dies. The star runs out of fuel. It collapses under its own immense gravity. It crushes itself down into an infinitely small point. This point is called a singularity. Diagram, event horizon. This is the point of no return. Once anything crosses it, not even light can escape. The pull of gravity is simply too strong. This is why black holes are black. But that is not the whole story. The region around a black hole is one of the most violent and energetic places in the cosmos. Matter like gas dust gets pulled in. It does not fall straight in, it spirals. It forms a vast, flat whirlpool called an accretion disk. Friction and gravity heat the disk. Temperatures reach millions of degrees. The disk can glow brighter than 1,000 galaxies. It shines with X-rays. It also emits other high-energy light. A black hole is not just a hole, it is an engine. It converts mass into raw, brilliant energy. The first and most famous idea for extracting this energy is called the Penrose process. It was conceived by the brilliant physicist Roger Penrose in 1969. It is a clever trick that uses the strange physics of a spinning black hole's ergosphere. Remember, this is the region where space-time itself is being dragged around. The process works like this. You take a package of matter, you throw it into the ergosphere, you aim it carefully. Just at the right moment, you split the package into two pieces. One piece is allowed to fall across the event horizon and into the black hole. The other piece is ejected back out. Here is the magic. If you do this correctly, the piece that flies back out can have more energy than the entire package you threw in originally. It seems like you are getting something for nothing. But you are not. The extra energy is stolen from the black hole's rotation. The part that falls in has negative energy relative to an observer far away. By sacrificing it, you are effectively slowing the black hole's spin by a tiny, tiny amount. You are mining the black hole's rotational energy. It is like throwing a rock at a giant flywheel. The rock bounces off faster than you threw it, and the flywheel slows down just a little. This process is not just a wild guess. It is a direct consequence of Einstein's theory of general relativity. The mathematics works. The energy is there for the taking. Over time, by repeating this process over and over, you could extract a significant amount of energy. You could keep doing it until the black hole stops spinning altogether. The total amount of energy you could get is huge. For a large, rapidly spinning black hole, you could extract up to 29% of its total mass energy. It would be enough to power a galactic civilization for eons. Of course, putting this into practice is another matter entirely. A second, perhaps more straightforward approach does not involve stealing the black hole's spin. As we saw, the accretion disk of a black hole can outshine entire galaxies. This is a fire hose of raw energy, mostly in the form of high-energy radiation, X-rays, gamma rays. The idea here is to build a structure that can catch this radiation and convert it into power. This concept is similar to a Dyson sphere, a hypothetical megastructure that would enclose a star to capture all of its energy output. But for a black hole, it would be a bit different. You would not build a solid shell. The intense gravity and radiation would tear it apart. Instead, you could construct a vast swarm of orbiting collectors. Imagine millions, even billions of independent power stations, all flying in carefully choreographed orbits around the black hole, far enough away to be safe. Each collector would have large panels like solar panels, but designed to absorb X-rays and other high-energy photons. They would convert this radiation into electricity. This electricity could then be stored or beamed back to where it is needed, perhaps using powerful lasers. This would be a decentralized, resilient power grid on a cosmic scale. The advantage of this method is that it is, in some ways, more passive. There is a third, far more speculative way we might get power from a black hole. This one comes not from classical relativity, but from the strange world of quantum mechanics. In 1974, Stephen Hawking made a revolutionary discovery. He showed that when you combine quantum theory with the physics of black holes, something unexpected happens. Black holes are not completely black. They should, very slowly, emit a faint glow of particles, Hawking radiation. Pairs of virtual particles pop into existence near the event horizon. Sometimes one falls in while the other escapes. This is incredibly slow for large black holes. A black hole the mass of our sun would take longer than the current age of the universe to evaporate. So as a power source, this seems useless. However, the theory opens up fascinating possibilities. The escaping particles are entangled with the ones that fall in. Entanglement is a strange quantum connection linking two particles no matter how far apart they are. Measuring one instantly influences the other. Some physicists theorize that if we could manipulate entanglement, we might extract information and perhaps energy from the black hole. We do not know how to do this. We are not sure it is possible. Laws of physics might forbid sending energy via entanglement. Still, Hawking radiation shows black holes are tied to quantum reality. While these ideas are thrilling, the practical hurdles are monumental. They are perhaps the greatest engineering challenges a civilization could ever face. The first and most obvious problem is distance. The nearest known black hole to Earth is named Gaia BH1. It is about 1,600 light-years away. A light-year is the distance light travels in a year, about 9.5 trillion kilometers. With our current fastest spacecraft, it would take tens of thousands of years to get there. To even begin, we'd need a revolution in propulsion technology, fusion rockets, antimatter engines, some other exotic form of travel to shorten the journey to decades or centuries. Then there is the problem of construction, not a bridge, not a skyscraper, a swarm of collectors the size of a solar system, or a machine that can operate inside a black hole's ergosphere. This would require an unbelievable amount of resources: mine asteroids, mine moons, mine entire planets, fleets of autonomous robots assembling megastructures in deep space. The logistical complexity would be staggering, a project taking many generations, possibly thousands of years. The level of technological mastery required is immense. Every component would have to be perfect. Dyson swarm collectors, keeping precise orbits for millennia. Machinery performing the Penrose process with flawless timing inside a hostile environment. Everything controlled by advanced artificial intelligence. Communication delays make human control impossible. Building the most complex machine in history and letting it run itself. Finally, the energy investment. It takes energy to get energy. Building ships, mining materials, constructing the power station would require colossal energy. A civilization would need to have mastered its solar system's resources first. A robust industrial base on moons and planets. Harnessing a black hole isn't the first step, it's the last. The ultimate graduation project for a species that has conquered its stellar backyard. Beyond the challenges of distance and construction lies the immediate and deadly danger of the environment around a black hole. These are not peaceful places. An active black hole, with its glowing accretion disk, is a source of intense radiation. It floods its surroundings with a lethal storm of X-rays, gamma rays, high-energy particles. Any machine, let alone any human, operating nearby would need incredibly heavy shielding to survive. Electronics would be fried, materials would become brittle. Black holes create extreme gravitational tidal forces. This stretching force, known as spaghettification, would be immense. Any orbiting structure must be far enough to avoid being ripped apart, but close enough to effectively capture energy. We must also consider the risk of catastrophic failure. A small mistake could have cascading consequences that we cannot fully predict. We would be playing with the most powerful forces in nature. Before we ever attempt such a project, we would need a complete and perfect understanding of black hole physics and the complex environmental dynamics. Even if we solve all the technical and safety problems, a set of profound ethical and political questions remains. Who gets to decide to build a black hole power station? This would not be a project for a single nation or a single corporation. The resources required would necessitate a global or interplanetary effort. How would such a massive collaboration be governed? How would we ensure it benefits all humanity and not just a powerful elite? The history of energy on Earth is filled with conflict. Would we repeat these mistakes on a cosmic scale? Who owns a black hole? The idea seems absurd. It is a natural object in the cosmos. But if one group spends millennia and vast resources to build a power station around it, do they then own the energy it produces? Can they sell it? Can they deny it to others? Access to virtually unlimited energy is access to ultimate power. A civilization that controls that energy could dominate others. This could create a new form of inequality, a gap between the energy rich and the energy poor larger than ever before. What happens when energy is nearly free and limitless? It could be a utopia. It could end poverty. It could provide clean water, food, a high standard of living for everyone. It could unlock incredible creativity, allow us to pursue science, art, exploration on a grand scale, but it could also lead to decadence and waste. If energy is no longer a constraint, will we be more reckless with planetary resources? Will we lose our sense of value and restraint? We've been observers of the cosmos, a tiny species on a small rock, looking out in wonder. To harness a black hole is to stop being just observers. It is to become active participants in the cosmic drama. It is to take our place as shapers of the universe. This is a profound transition with immense responsibility. Are we wise enough to wield such power? Are we mature enough to manage it without destroying ourselves or the cosmic environment? The prospect of powering our world with a black hole is a stunning vision of a possible far future. It is a future where humanity has transcended its limitations, mastered the laws of physics, and taken its place as a mature spacefaring species. The energy from a single black hole could light up our civilization for millions of years. It could fuel our expansion across the galaxy. It is perhaps the ultimate technological aspiration. But it is important to remember that this is a distant dream. It is not a solution to our immediate problems. The challenges of distance, engineering, safety, and ethics are almost as vast as the universe itself. The path to that future does not begin with building interstellar warships or Dyson swarms. It begins here and now. Our immediate duty is to solve the energy crisis we currently face with the tools we currently have. That means investing in and deploying solar, wind, geothermal, and other renewable sources as quickly and as widely as possible. It means improving our energy efficiency and building smarter grids. It means continuing to invest in research for cleaner, safer energy sources like nuclear fusion, which could provide a crucial stepping stone. At the same time, we should not abandon the grand vision. We must continue to push the boundaries of science and exploration, invest in fundamental physics, build better telescopes, and develop new propulsion systems.